Thanks, everybody, and I'm super excited to be here. One of my favorite things to do when I look towards the future is look to the past and study the history. You can learn a lot, and you'll see that theme throughout our conversation today as we talk about context engineering and how hypersearch and real-time analytics can be brought to strengthen a practice that's already picked up a lot of steam. So, a little bit of pun. Let's start with some context first, just to make sure that we're all working from same basis of knowledge. So context engineering is somewhat of an ambiguous term. And the way I see it is really about building the right information pipeline so an agent or agentic model can understand context to make decisions. If you look into the not so distant past about data engineering, it's all about building the right data for humans to make decisions. So you can kind of see a lot of the things that we encountered in data engineering, you will also see in context engineering. Let me kind of illustrate that a little bit. So you all have to deal with ingestion, getting the data from where it's generated. Same thing for context. Context is constantly being generated. Just your conversation history with your agent is context. Your information about your enterprise is context. The video frames in a self-driving vehicle is context. So we now have moved from purely tables to more multimodal things that require a different set of tools to look at. When we talk about data engineering, you often have to deal with a database. And we're going to talk about a lot about databases today because that's what Apache Doris is. So when you're dealing with databases in a data engineering situation, you also have to deal with a data store or a context store in the context engineering. And oftentimes, the problems and the challenges that you see are very similar. Finally, there's governance, and there's also serving. You have to serve the context to something. Sometimes this is an agent or through a variety of different interoperability interfaces. Same thing for data engineering. And for governance, you have data governance. And now we have AI and agentic governance. So hopefully, this will allow us to see that there's quite a bit of similarities if we just look a little bit in the past. Now, you might ask, why is this important? Well, agents and AIs is really only good as the context they receive. If you are grounding your agents to context that's too old, too stale, or incorrect, you're going to get information and outcomes that are not to your liking. And RAG system, although people think this is an old concept, if you look closely, modern retrieval systems still build on the basic concept of finding relevant information to enrich into LLMs. In a lot of cases, this can be viewed as context. And retrieval quality directly impacts AI output quality. So that's why we're really focused on building the right context, using cost-efficient resources, boosting accuracy, and then bring the real-time need because as data engineering evolved from batch to real time, so will context engineering. So if we look at the landscape of context engineering, I briefly mentioned a few clusters of activities and workloads. We start off with chunking and embedding. This could be splitting documents into semantic chunks and then convert them into a vector embedding with an embedding model. This can be looked at as ingestion and cataloging. Then we have the context store retrieval. So now that data is sitting inside a data store, this has to be served to the right place at the right time with the right accuracy and also done in a cost-effective manner. This will be the focus of our conversation today as we look deeply into this retrieval layer. Some other things I wanted to also point out are the memory management layer because, as I said earlier, as you're using agents, you're also generating context. And talk to me afterward about what we could do there. We have some really cool project called Apache Doris Lightweight, built for embedded to serve this problem. But today, we're going to leave that aside. And then finally, there's the routing and orchestration. Some intelligence has to tell the agent what to do. There's intelligence that you may need to create the context mapping so that you're modeling things correctly. This is also out of scope for today, but very important, and I think this is where a lot of advances are being made very quickly, which is why our models and our harnesses are getting better, not because the models are necessarily getting bigger, but we're more intelligent about using them with the right workflows through these orchestration and routing. Also, I want to give a quick refresher just on vector search, on full text search, as we're going to dive into some of the challenges in this space. So vector search, really from a meta paper that was published on augmented generation, is the basis for retrieval. So we basically look at a whole bunch of information, and we want to map out some similarity between this information. This isn't exactly new, actually. We've done this in marketing for decades, where we find information about a person, and we find similar persons, and we try to map them together based on their attributes. So we took that concept and moved it for similarity retrievals. In this case, we take some sort of data, most likely documents, which is the most common use case. We break them down into pieces, and then we use a model that understands the similarity of these different pieces and put them into an embedding. So think about this as calculating distance in a high-dimensional space. We all do this in three-dimensional space, except now we're doing it in dimensions that are in the thousands. And when you search, you're really looking for clusters of similar things. So for example, cat and kitten, very similar. So the distance in the embedding is also very similar. So when you retrieve the distance, it's going to be a short distance, and it's going to rank high in terms of the retrieval preferences, or what the model thinks that you will need in terms of information. So hold that thought for a second. At the same time, vector search, which is based on approximate nearest neighbor, is not precise. It will only give you what it thinks is close. The other way of doing this is using something called full text search, which gives you precise retrieval on the exact match of what you're looking for. So if I'm looking for like a keyword called error, it will find the keyword error. It will not find semantically similar things to error, like wrong or not correct. It will find error. And the way this works with inverted index and BM best match 25 scoring is it looks for how often something appears, how rare it is based on the overall corpus, and how long a document may be. And I'm not going to go through the math today, but here's the formula for calculating the scoring for what this thinks. Like vectors, you have a score. BM25, you have a score as well. So now that we got these two concepts out of the way, what's wrong with vector search as the form of retrieval for context engineering? Well, I alluded to this a little bit earlier. If you have things that are semantically similar but doesn't match your intent, for example, San Francisco and Seattle, both on the West Coast, semantically similar, not what I'm looking for. So if you're doing a pure vector search, you may run into semantic confusion there. The second thing is indexes is large. And in many cases, if you want your retrieval to be performant, you have to load the entire index into memory, which requires large clusters. Something like a billion vector may take about 20 terabytes of memory. We'll dive into detail for that in a second. Memory has been really expensive, so we don't want to spend more money than we have to on just RAM. And then finally, filter failures. If you have specific things that you're trying to look for, maybe there's a date range, maybe there's a category, maybe there's something that's already deterministic, you don't necessarily want to use expensive vector search to do that. There are other cheaper ways that you can do that. So oftentimes spending that extra compute to trying to get to that precise result is not the most efficient way of approaching this problem. So there is a better solution. Many have implemented this solution. It's called hypersearch. So we combine different search methods using keyword search with exact matching and vector search with semantic mapping. And then we can take the score from both, rank them to see which one is actually more useful to me, and then use the results for that as the context retrieval result for me to go feed my agent for the next step in decisions. This is great because it allows you to get precision as well as the semantic retrieval, improves accuracy significantly, but there's still some challenges on the implementation side. So early on, if you were to do this, you may have to use multiple databases. You may have to do searches in parallel, duplicate your data, and then rerank the score separately. Oftentimes, there's the score fusion. So how do you actually take these different scores, especially for large deployments? Because one of the quirks for BM25 is if you're working in a sharded database, you're going to have inconsistent re-ranking. Depends on who did the search on which chunk. So there's some confusion there as well. And then there's the issue of cost at scale. For every layer that you add, for every database that you add, you're adding complexity. And some systems are able to address some partially address this problem, maybe combining full text search with vector search, but it's still unable to do SQL well. And filtering with SQL is still the cheapest thing that you can do. So we understand that hypersearch can help us. So a lot of people are doing this, but this is still challenging. So what can we do about it? So this is where Apache Doris comes in. This is a unified real-time analytic and search database. And I'm going to talk a little bit about this project. It's been around for a while. And it is also the technology behind our company. We'll talk about that at the end, or find me at the booth. So this is a community-driven project that came out of Baidu. It graduated Apache project in 2022, has a ton of contributors and enterprise users, very vibrant community. But for today, I'm more interested in how we create technology that's able to address this challenge. And it has a rich history. It started in 2008, addressing the challenges of real-time analytic. Back then, we had Hadoop systems. There's a ton of dependencies. You're dealing with Zookeeper, you're dealing with Hive, you're dealing with MapR, you're dealing with all sorts of really things with heavy dependency chains and difficult to use. So Apache Doris initially born out of that to consolidate a lot of that. No dependency, simple to get started, real-time performance, fast ability to write the data into the data store, and then fast read of that data so that you can have a data freshness at the second level. So again, coming back to a history a little bit, right? We started with batch, we consolidated things with lakehouse, but there's still a real-time need. This is where that comes in. Speaking of lakehouse, we also recognize that over time, we don't really want to move data. We want to consolidate. The promise of the lakehouse is to really share data so that we don't have to pipeline it from A to B and B to A back and forth based on who's using it for what purposes. So we adapted that architecture as well. But then as we go on this journey, a lot of customers started asking the question of, hey, or users, I'm doing log analysis with a lot of text data. And I need to take that data and join it against my metrics. I need multiple databases. Wouldn't it be great if I have one database that can do both? And we thought, okay, if we added some indexes, inverted index and BM25, we can handle that workload. And then if you keep going down that train of thought, if you already added full text index, the next workload is for vector indexing. You can do the same now for documents because you're already working with this modality of data. You just need to add a few more indexes to be able to handle this workload as well. And that's what happened in the last year. So as of now, this is fully GA for 6 months. We have many users that are using this Apache Doris for the real-time analytical stuff, dealing with tables and source of truth, logs for observability to be able to simplify how they're processing their data in real time across 2 modalities. And then now, in the AI era, with model companies, as well as people that are trying to build agent, storing all their contextual information that could be coming from images or documents with their source of truth, their tables, and their logs, consolidating all the context that an agent may need into one place, unifying where you store your data for the data engineers who need to serve this to a human, as well as the context engineers who need to serve this to an agent. And just really quick, some new things as of 2025 and 26. Vector search, JSON and semi-structure, we actually support variant as well, so you can actually do things in a performant manner. And then additional indexes that we're continuously adding to help users really get the most out of the hybrid search and the real-time context engineering use cases that they're currently working on. So hopefully that gives you a little bit of a history about Apache Doris, our thought process and behind the decisions we made to advance the project, always looking at what people are doing while delivering the core principles of simplicity, real-time performance, and unifying analytics to minimize the operational overhead. So On hybrid search specifically, what are we doing that's a little bit different? Speaking to those principles, we start with the unified data layer. Whether you're running analytics, vector search, or keyword search, or wanting to join your analytics to the context retrievals, you can do this in one system. Because the data is stored in one place, you can retrieve all of the data through SQL, sometimes performing all three types of search in a single statement. It makes things easy to find the data in the context you need. We also built in re-rankers, and this works in different ways. You can do things in parallel or in series, which you can form something called a progressive filtering. These are done for different purposes, and we'll talk about the power of progressive filtering in a second. And that's all about minimizing the problem space, reducing the dimension space we're working in so that we can actually be more efficient with compute, which leads to the scale with efficiency aspect of it. Because Apache Doris was born for scale. It was designed to handle high concurrency, large amounts of data, large amounts of horizontal and vertical scaling. So we take scale problems very seriously. And there's a lot of optimizations and tricks that we do to help with that scale. One being the progressive filtering, how to handle large workloads without ballooning your infrastructure. And second of all, what are the techniques, indexes that we can do to, again, reduce the problem space? Starting with things like IVF index, product quantization, and some clever way we can save memories in a real solution that I'm going to explain in a second. So now, getting to the real world example, hopefully this adds a little bit of color on how someone can use Apache Doris to solve the problems I just described. So one of the users that we're working with, and they're also a contributor to the project, is ByteDance. They needed to build an internal system with 10 million documents and about 1 billion vectors. And they need to do this efficiently, and to serve high QPS. Some of the challenges, these should look familiar. So when they first used pure vector, HNSW, they were getting about 58% relevancy, which is very poor. And they were getting that exact situation where they're looking for people in San Francisco, and they're getting a lot of people from Seattle, and they're wondering, why is this happening? They also had unstable ranking. Different people querying different part of the database, part of the shard, getting different results because the statistics is not global. And they did an estimate if they were to use their current HNSW index for 1 billion vectors, they would need about 10 terabytes of RAM. That's 20 to 30 servers, and could cost millions of dollars for this particular task. So it almost becomes that the ROI here just isn't worth it because it's too expensive for the benefits I'm getting. And some of the details regarding these problems, like I said, when they're looking for Python developers, the root cause is San Francisco and Seattle. Distance is very close in vectors. And 5 years, 2 years, years very semantically similar. Because they're looking at resumes, they need to be very precise. They really want 5 years, not 2 years. They need to be able to precisely get these deterministic outcomes after looking for the semantically similar experiences that they are also looking for. Memory explosion, so unpacking why it took 10 terabytes to actually fit all of this in. It's 2.9 terabytes for the raw vectors. And then when you use the HNSW index with the multi-layer traversals, it adds another 7 terabytes. And all the graph connectors adds a little bit of data as well, looking at about 10 terabytes of memory that you need. With the ranking stability, depends on which chunk they're looking at. They're getting different BM25 scores, and that is causing results that being not stable. So the solution that we come up with working with this user is progressive filtering with hybrid search. The first thing we did is saying, hey, with a simple whereby clause, we can probably filter out a lot of the problem space that we don't need. This is done with just SQL. That immediately reduced the problem space down to 5 million vectors that we had to deal with. And then we performed keyword search filtering, looking for the exact things that we don't want in a negative filtering, and also the exact things we do want, so that we're able to reduce the vector space down from 2 million to 20K. And if you see the difference between the structure filter and the keyword filtering, that's because we're looking at slightly different chunks in there. Then we have vector search. So now when we get to the vector space, we're relying on vector search. It's a much smaller dimensional space. Instead of looking at starting with 1 billion vectors and searching that, or even 2 million vectors for searching that, we're left with 20,000 vectors. Some of the things here is that if you can fit all of this vector into an L3 cache, you don't actually have to perform a vector search. You can brute force it. You can scan all of the vectors and just simply find your answer. And then, of course, at the end, we re-rank everything and serve the top 10 so that you're getting the benefits from using these different indexes and searches. So diving into some of the solution in a little bit detail. One of the indexes that we use is the inverted file index clustering. So instead of searching for 1 billion vectors through the different layers, we cluster vectors that are similar together so that we're not searching through the entire vector space. You can actually look at relevant clusters and then search that cluster. That reduces the dimension space by itself. And this is for if you actually want to purely search for that vector, because there's some use cases that you would have to do that. We also use product quantization. I think this is a lot more popular now, where you're actually reducing the vector dimension space. So we're compressing a lot of this down to by using a codebook. So basically splitting the vectors into subvectors with smaller dimensions, and then we train a codebooks to point to the subvectors based on the representation of the quantization. So think about this as like product quantizations in marketing with dimension reductions. So if you have, let's say, 100 dimensions that you're describing somebody, maybe only 10 of those dimensions actually moves the needle. The rest of them is simply noise. So you can actually reduce the dimension space down to 10, look at the signals that the strongest that's actually moving moving the needle on what you're looking for, like actually distances that are closer, things that are actually relevant to what you're trying to answer. Then you're looking at that smaller space, and it's much more efficient to be able to do that. And we're doing this through built-in product quantization. You can do this to an 8-to-1 ratio, or you can do this to a 4-to-1 ratio. It depends on your SLAs for your retrieval systems. Then we have re-ranking with global statistics. So if you're doing the calculation for BM25 and use the global statistics, you can be sure that this is actually going to give you the same score, no matter which chunk you're searching for, because the length of the document, the frequency of the term, and how rare these terms are now using consistent statistics rather than local statistics. So putting all of this together, what is the actual outcome? So here, where we're able to achieve a 95 percentile of 400 millisecond latency. So this is actually 7 times faster than pure vector search with HNSW for this particular case. We only use 500 gigabytes of memory. This is also 20 times less than using a pure vector search. You can fit this on a single server. So think about the savings there. It's also more accurate because you're now no longer hitting semantic confusion, and you're also using global statistics for re-ranking. So this is actually a 7-point accuracy improvement over pure vector search. So overall, very reasonable latency, efficient resource usage, and more accuracy by using a series of search techniques rather than just vector. So now, that's the power of using hybrid search as a retrieval solution in context engineering. There's also still the need for real time, because as we get better at building agentic systems, we're going to apply it to situations with SLAs that are in the seconds and no longer batch. Today, we're still in that batch mode. If your data changes or your context changes, let's say a document changed. Maybe this is a support ticket that somebody added an additional comment or added a comment on. You would have to re-chunk the entire document and re-ingest everything. That doesn't have to be the case. There are actually partners that we're working with that allows you to do this in increments. If one line in that document changed, you only have to re-ingest and re-embed that single line because it's done in a stateful manner. However, if you look into the past with streaming, Your stream can be really quickly, but you still need a solution that writes that stream into a database fast. If it's not real-time or fast end-to-end, you will get bottlenecked. In this situation with real-time context engineering, as we get better at updating things in increments, we also need to be able to write data into a knowledge stores just as fast. And that's where Apache Doris really shines with its real-time capabilities. As the streaming data needs to be searched within seconds, we can write that data within seconds for you to run analytics and search on. And we don't have to do a full rebuild. Working with tools like Cocoa Index, we can do a partial rebuild just on the deltas. And eventually, a lot of the retrievals will need to be done in multimodals, so you really need to think about where are you storing all your data. Do you really need multiple databases for each modalities? That's called polyglot persistence, and there are multiple camps. One camp says you need dedicated database. The other camp is saying, well, if I'm dealing with real-time needs, latency matters, multiple databases only add to that. A more unified solution will actually allow me to achieve my goals rather than dealing with multiple databases and the data sprawl that comes with it. So hopefully this talk is interesting to get some of you to think about how you build agentic systems going forward and how we can deal with real-time engineering today rather than dealing with it as a Band-Aid in the near future. Thank you, everybody, and happy to answer any questions.